in the computational basis. So what that lets us do is we'll be sampling from the coordinates of the particles according to the absolute square of the wave function. So this is really just like doing a measurement in the position basis, where what's the simultaneous position of all these electrons and nuclei, and we're just going to sample from that probability distribution. Now we could also do a Fourier transform and then a measurement as in the computational basis. At that point, you're now doing the same thing except in the momentum basis instead of the position basis. So you get a sample from a probability distribution over a momentum space given by the momentum space wave function, which is just the Fourier transform of the position space wave function. But a lot of times, as we know in a physics class, we define our measurements based on an operator. We have some operator, and we want to measure in the eigenbasis of that operator. And it turns out there's a nice general trick due to Kitaev, which allows us to do that as long as the unitary transformations e to the minus iht are always simulatable where our operator that we're trying to measure in the eigenbasis of is h. So I've written it as h as though it's a Hamiltonian, but it doesn't necessarily have to be a Hamiltonian. It could be any Hermitian operator. It could be a momentum operator, some kind of angular momentum operator or whatever. But I'll just call it h for now. So let's see how the phase estimation algorithm works. So this is the circuit diagram for it. And I'll have to explain this. This is not a standard notation. This is something I just made up. And what it is we have some value written in this register, just written out with place value. And we do a controlled unitary e to the minus iht, where t is the value that it finds here. So after we do that, we exactly get this state, sum over, we start with a superposition over t's. I've omitted normalization here. And then e to the minus I energy t for psi. So imagine, for example, psi is an eigenstate of h with energy e. Then this is the state that we would get. So then, again, we take advantage of the fact that phases are not tied to any particular register of qubits. They're just a property of the state. We can commute this out front, and we can view this part as being like a plane wave. So when we Fourier transform this is exactly the thing that gets taken to the basis state t, where Fourier transforms are transforming between the plane wave basis and the computational basis. So now, if this is an eigenstate, this is our state. So I've commuted this phase out front. We Fourier transform now e. This eigenvalue is written in this register. We can just measure in the computational basis and read it off. So that's phase estimation. Yes?
Is there a mismatch between the continuous aspect of time in the Schrodinger and the discrete aspect in the summation over t?
Yes. So what you need to do here is you choose some number of bits of precision for this. And there are two aspects of that. Let's see what I'm trying to say here. Basically, if you choose this superposition to run over too small a range of t, then basically it's just like the energy time uncertainty principle. You're making this is not so this is not the state, integral 0 to infinity dt e to the minus I e t t, which if you Fourier transformed it would give you the exact value of e. This is over a finite domain. So it's kind of like if you take this plane wave and you cut it off with some envelope function, the Fourier transform of that envelope function is going to convolve with what you wanted, which was an exact delta function, and you're going to get some uncertainty. So how many bits you put in this register determines how precisely you can measure this eigenvalue. Okay, so now I've used this primitive here, which is given t written in binary place value, we want to evolve for e to the minus ihts. How do we implement that? Maybe you can think about the tools that we've seen so far to see how this goes. The answer is you can just build it out of e to the minus iht over 2 over 4 over 8, all to the powers of 2, and then do controlled operations here. So now whatever number is written in binary in these bits, then that's the corresponding amount of time that will simulate h for. And then each of these controlled operations, we've already seen this is some arbitrary quantum circuit. We replace it gate by gate with the controlled versions. Now those are 3-qubit gates, and we know that 3-qubit gates can in turn be decomposed into 2-qubit gates. Okay, and we need to make the uniform superposition over t at the beginning. Well, we've seen this problem before. We can apply a Fourier transform. It takes the all zero state to the uniform superposition with no phases. So it's just like making the phi m state, more or less. Actually, we don't need anything as fancy as that. We could just apply a Hadamard gate to each qubit individually, because you can see that if we have the superposition of these numbers, 0 to 2 to the n, then that's just a tensor product state of the uniform superposition on each bit, so we can just use Hadamard gate on each bit to make all of those. Okay, so excuse me. So far I've neglected spin. Now let's go to the other extreme and look at a pure spin Hamiltonian, neglecting spatial degrees of freedom. So maybe we have spins on some lattice interacting according to some Hamiltonian composed out of Pauli matrices. So this is just not the completely general type of this Hamiltonian, but as one example, you might have like an Ising model with some transverse field. So how could we do this? Well, one way we could do this is we saw already the Trotter formula where we just have two Hamiltonians, A and B, and the same thing holds more generally if we have a sum of k Hamiltonians. So if we have e to the minus ih1 plus so on plus ihk, we can just apply these sequentially for short times, repeat that over and over again, and this will approximate what we would get by applying all these things simultaneously if we choose n large enough. And in this case, n, we have to choose it to scale quadratically in both k and t, although there are also higher order formulas that do better than that. So then what about these individual factors? Now we've reduced our problem to just simulating the time evolution induced by, say, one sigma x term or one sigma z coupling. Well, we know we can do that just by, again, invoking our big hammer of gate universality, that such a thing, say a sigma z coupling, is just going to be, it's only acting on 2 qubits. So this is some 4x4 unitary. We can make all of those. So now we know how to simulate the spin systems. So everything I've said so far has been in a first quantized formalism. And if you're simulating using that point of view, then the problem of fermionic and bosonic statistics is ultimately a problem at the state generation stage. If you make your initial state at the beginning symmetric, your Hamiltonian will never take you out of the symmetric subspace. If you make it antisymmetric, your Hamiltonian will never take you out of the antisymmetric subspace. And this is kind of an advantage compared to one of the many advantages compared to classical computation, because classically, if you're doing imaginary time evolution, you're preferentially driven into the lower energy states. So if there's some way of leaking a tiny bit out of the antisymmetric subspace, say, due to some imprecision in your simulation, then very soon you'll just be driven completely into the symmetric subspace, and everything will all your answers will be wrong from your computation. But that's not true in the quantum case. Everything is completely linear and unitary. So then how do you prepare symmetrized or anti-symmetrized states? Well, I am not going to go into that, but there's a nice paper by Abrams and Lloyd, which the reference I give here. I'll try to post these slides somewhere, so if you want to look at these references, you can. And they show how to do this. Sometimes the second quantized representation is more efficient. There's a lot known about choosing good basis sets and so on to improve your simulations that is kind of drawn from the classical quantum chemistry community. And in the second quantized representation, bosonic statistics are trivial because you just need to say, well, this mode is occupied or unoccupied, and you just write a 1 or a 0 there. The fermionic case is a little trickier, but there's, again, some clever tricks, these, in this case, from Bravi and Kitaev, for dealing remarkably efficiently with the fermionic statistics in a second quantized point of view. Okay, so to summarize, I guess I have 15 minutes or so. Is that right? Okay. All right, yes, I have some more. So, but before going on, to summarize the main content, I've introduced the quantum circuit model, which we compose from elementary gates. And these are just unitary transformations acting on a constant number of qubits. We can define that constant to be anything we want as long as it's at least 2, and that doesn't change the model of computation. We can make any unitary transformation on those n qubits by composing sufficiently many gates. That can be a useful tool. That construction can be a useful tool to make little blocks on logarithmically many qubits, as we've seen. But in general, you need exponentially many gates for n qubits. But this very seemingly limited model seems to capture the dynamics achievable in laboratories, the time evolutions of spins, the quantum chemistry type problems, essentially any problem you can think of, so far seems to be decomposable as polynomial compositions of these elementary gates on qubits. And so for the rest of my lectures, I'll just use the quantum circuit model as kind of our definition of what a quantum computer is and how to measure the runtime of quantum algorithms. Yes?
These models capture the dynamics after an approximation, right?
That's right, yes.
So what was the nature of that? Was it a polynomial approximation? Or?
Yes. So it would only be in special lucky circumstances that you can approximate things exponentially well.
So this approximation, is it because you discretize your field space?
Yep. So there's a number of approximations involved. First of all, using finitely many qubits to write down your spatial coordinates or momentum space coordinates of your particles. That's one. Another approximation comes from the Trotter formula, which is, in a sense, a way of discretizing time. And I'd say those, and then there can be additional approximations made by taking some arbitrary low-dimensional unitaries and decomposing them approximately into a discrete set of elementary gates via Solovay-Kitaev. So those are 3 of the most common sources of approximation. But basically, the definition of simulation that you probably want, the most natural one, is that your measurement, the probability distribution you sample from at the end of your computation, should have small total variation distance, like 1 over polynomial total variation distance from the true probability distribution. And I think that's what I'll mean when I say simulation. Another thing you could mean about simulation is, well, which I would never use the term this way, but some people do, is let's say I want to find the ground energy of this Hamiltonian, or I want to find the ground state, or some ground state correlation function, or something like that. In general, you cannot necessarily expect quantum computers to efficiently solve that problem for the same reason that nature doesn't necessarily efficiently solve that problem. It can get stuck in metastable states, much like Scott's soap bubble example. And in fact, we know that those problems in general have a property called being QMA complete, which is sort of the quantum analog of NP complete. That if you could solve a QMA complete problem efficiently on a quantum computer, then that would mean that any problem whose answer you can verify efficiently on a quantum computer, you could also just directly solve on a quantum computer. And that's considered very unlikely. Another one of these conjectures which are widely believed. Mm-hmm.
So when you talk about simulating a quantum system, I think the sense you were talking about here is, you generate some quantum state where in the end, if you do measurements that are fairly straightforward on it, you'll get the same probability distribution that you would have, from the actual system you're trying to simulate.
Mm-hmm.
You could also be interested in actually just, you care about the expectation values rather than being able to just draw from the ensemble. Can that be a source of making it much more difficult in general, or is it usually also easy to, if you can simulate, then you can also get the expectation value out as a number?
Yeah, well, as long as you don't have something weird like some weird ultraviolet catastrophes or something, what you can always do is just use phase estimation of your operator repeatedly. Then you're sampling from a probability distribution over the eigenvalues of that operator. And then if you average what you get from those samples, that's a statistical estimate of the expectation of that operator. And you do that n times to get an estimate to within 1 over root n.
Way you measure a probability
Yeah.
distribution.
Right. Maybe I could comment. It's actually the other direction that's much more problematic, right?
Yeah.
From being able to estimate any expectation value, no one knows if that would let you sample the distribution. Yeah.
Mm-hmm. Yeah, it's a good question.
Yeah.
Yep.
So you said you could get exponential accuracy only under rare conditions.
Uh-huh.
I'm not sure what that meant. There's this recent result by Bear, Childs, Cleve, Selma, maybe somebody else. They say that you can get scaling of the number of gates with the accuracy, which is log 1 over epsilon.
Yeah, that's true. Yeah, that result was surprising to me. I may have failed to incorporate it into my statements. Yeah, that's a good point. It's a very interesting, very recent paper where they use Trotter formulas, only first-order Trotter formulas, but supplemented with extra tricks so if you want this difference to be epsilon, the number of the gates they use scales only like log 1 over epsilon over log 1 over epsilon, which is quite amazing. And to me, it's the kind of thing that is not really dictated by the Church-Turing-Deutsch principle. It's something extra that just, it turns out to be possible and some smart people discovered it. So.
If you wanted to simulate a dissipative system, I know that
Yes.
would be a fundamental physical system. Can you? What would happen if you tried to use a quantum approach?
Well, I think basically that is a very interesting and only lightly investigated area of open research. There are a few papers about this, but I think the understanding of that is still much more spotty and less systematic than what we have for closed systems.
What you wouldn't buy in a free space, right? I think with a dissipative system, it's very likely that you go outside of you couldn't confine yourself to a specific region. That's what you get with radiation and specific problems.
Yeah, I mean, one thing you can do is,
So you can't define application in this specifically.
yeah, I mean, there's a few statements you can make off the cuff about dissipative systems. One is that for a completely general environment that you're tracing out and looking at the reduced dynamics on what's left, you shouldn't necessarily expect to simulate this efficiently because a completely general environment could be some arbitrarily large quantum circuit on as many qubits with as many gates as you want. And if you're tracing that out, in the general case, you shouldn't be able to do anything better than actually just simulating the whole combined closed system. But on the other hand, if you have something that's more of a simple environment, like some thermal bath or something, then maybe you should feel that, well, probably there's a way to simulate this, and maybe it would even be easier to simulate than a closed system because it's somehow less quantum. But there's, and there are a number of isolated results, I think, of this type, but I don't think there's like a complete picture of how to characterize this yet. One interesting case, I guess, is something called the one clean qubit model, which I'll talk about in my third lecture. And in that case, what you have is you have one qubit in a pure state, and you have n qubits in the maximally mixed state. Then you apply whatever polynomial size quantum circuit you want to that combined n plus 1 qubit system, and then you do a single qubit measurement at the end. And this was originally introduced because people were talking a lot about NMR quantum computers, which are acting on states that have pretty high entropy. And some people said, well, these states have almost no entanglement, and we think that probably it's not really quantum somehow, that probably this could be actually simulated by classical computers already. So then some theorists, Manny Canilla and Ray LaFlamme, introduced this one clean qubit model as sort of an extreme version of that and a mathematically clean idealized version of that, and argued with some examples that even in this case there appeared to be some problems that you could do with a one clean qubit computer that were not obviously doable classically. And so in my third lecture I'll give a couple examples of that, which turn out to include estimating Jones polynomials of certain knots and three-manifold invariants of a certain class of three manifolds.
So in the model you allow exponentially many gates in general, right? So what are the rules? What are the rules on my resources?
Well, in a sense you allow as many gates as you want, but what you're trying to do is use as few gates as possible. So a more successful algorithm designer is someone who uses fewer gates. There is a special case where you restrict yourself to polynomially many gates. The class of decision problems, yes or no type problems that are solvable using only polynomial gates is called BQP. And so there's a lot of work on characterizing BQP, showing that certain problems, such as factoring, the decision version of factoring, are contained in that class, trying to argue that certain problems are not contained in that class, trying to argue that that goes beyond classical computing, that it goes beyond NP, although it doesn't encompass all of NP. And there's a lot of argumentation specifically about what you can or cannot do with polynomially many gates.
Perhaps you're answering above the level of my question.
Oh, okay.
If I want to do, say, classical simulation of a quantum system by classical computers, then
yes.
If you allow me enough memory,
that's true.
Then I can also do that. So what?
Right. So here that's right. So all of the algorithms I've had in these slides have been ones that only use polynomially many gates, polynomially many quantum gates, as a function of the number of degrees of freedom of the system that you're simulating, and as a function of the amount of time that you're trying to simulate the time evolution for. That's a key point. Yes. Right. So I have not given the circuit for that, although I think maybe I have it in my lecture number 2, which I do have 5 minutes. I could show you that right now.
I wasn't asking for it.
Yeah. Okay. I won't then. You'll see it tomorrow. Oh, well, there's one more. Well, go ahead.
I had a question about universality.
Yes.
So I know that there are canonical sets of gates that people use in general for universality things, and I know that it's usually pretty easy if you can figure gates that are universal to show that they are universal. But I believe the opposite is not true. Is that true? It's actually difficult to show that a set of gates is not universal.
Yes, that's right. And it's a little bit tricky because you have to be careful about how you define non-universal. So, for example, if you have as your gate set only the Toffoli and the Hadamard gate, in a certain sense, a very strict sense, that's not universal because those gates consist only of real numbers, so you'll never get outside the set of orthogonal matrices. However, they are, in a more common sense way, universal because they're universal in the computational sense. If you start with some quantum circuit made from a standard universal gate set, you can always compile it into something out of Hadamard and Toffoli that simulates it efficiently in terms of giving you the same output statistics. So proving non-universality is both hard in practice and also not trivial to define.
Well, I mean, one definition that people often take in practice is that it's not universal for BQP, and in particular, we'll be happy as evidence for that if we can just show this set of gates can be simulated in classical polynomial time.
Yes, that's right. Although there are also, if you look in practice at the papers like this, there's some subtleties there too, because there are different notions of classical simulatability, such as getting the values of expectation values of operators as opposed to sampling from the output distribution. And so if you can just estimate expectation values, then that's, in my view, not quite full ironclad proof of non-universality, although it is very suggestive.
When we try to simulate Hamiltonian such as T plus 3, it's actually infinite metal systems. Can you just use continuous variable systems which has infinite degree?
Yeah, so I've avoided I've avoided continuous variable computing because in the discrete case there's a lot of things like the threshold theorem that you have, which can give you a lot of confidence that you're not fooling yourself. In the continuous variable case, you have to be very careful. Even classically, there have been examples where people showed that some analog computer could, in principle, solve some problem that with a digital computer would take exponential time. And then later other people analyzed it and realized that these analog systems would require exponential precision in order to achieve that speed up. So this is the reason that I've shied away from talking at all about the continuous variable stuff, but it's nevertheless an interesting subject, and there are some papers on it. I actually don't know that much about it. All right, I guess I better stop now.